Hello there. Do you ever got a sign wrong on something and that caused you to have all your work to get spoiled? Well, that just happened to me. I want to prove a theorem. Now I'm gonna have to go and look it up. Just pause this now. Whoops. Now I got confused in the system tray. Okay, I found it. No, I've never memorized this because I have a bad memory for one thing, and I don't like to memorize these things. I like to be able to work them out when I can. Now this is I'm sure you know from high school, called the Rotation of Axes Theorem. For a point in the plane, vector could have done that in one line, but sorry. Oh dear. Okay. Now the idea is this. If you rotate the axes some amount, or if you invent a new coordinate system like this that's at an angle to the current one, theta, which I will indicate in a second. Is that perpendicular about? It's not bad. Now, if this angle is theta, here's the theorem. I should write it. I'll write the theorem here. Maybe I should write. I'll put the theorem here. It looks more like a title. Now, in terms of we're calling this the x prime axis. And here the y prime axis. I have to define my terms. And I've always had trouble proving this, reproving this. Should use a different color for this. I'll use a brighter gray. And that's the y-axis. Okay, here. Okay, here's the x-axis, here's the y-axis, and here's the x prime and y prime axes. Okay, now there's two ways to state the theorem. One is first, P has a position x, y, which I will indicate with a line. The color line. I'd like to make a thin line, but I don't have that option. So I'll use this ugly color. Now that's 164. So the height here is y. So it's y. That's a problem with my sprites. And the distance from here to here is x. which should be 124. Okay, that'll be ready. Oh, come on. Approximately here. 4 stuff. Who ever thought this was a good idea? Why is that saying 120? Yeah. Alright. Those are the distances. So this here is x. And so those are the coordinates in one coordinate system. And in the prime coordinate system, there's x prime, darker color. Oh dear. Gosh, it's probably better that's there for now. Okay, now that would be if you were viewing it from the point of view of someone in the prime world, approximately here, let's say x prime and y prime would be a position about here, let's say. We follow parallel to the x prime axis a line to about here. Then that's his y prime coordinate. You see? And the theorem states the following. Like I said, I've never memorized it because it's one of those things that there's a sign involved and you always get the sign wrong. And first I'll write x and y in terms of the primes. X equal x prime cos theta plus minus, see, this is where I would get screwed up, y prime sine theta. I know that it's always cosine sine. That much I know. But as far as the signs, I can never remember which is which. Okay? And y is equal to x prime sine. You can see why, well, if you knew me, you would know immediately why this is a problem for me. Because it's overly symmetric. There's too many ways to get it backward. And I'm looking at it here and it's, I don't know. Is it right? I don't know. And then when it used to be that when I'd go and try and prove this for myself, I'd get all messed up. And it would take a long time. And I'd be very unhappy with the proof. But anyway, that's the equation for x and y in terms of primes. So these things toggle and the sign is toggle and so on. And you can write x prime and y prime in terms of the x's this way. X prime equals x cos theta plus y sine theta okay. Separate them. I should have put a different color, really. it's pretty spaced out. Y prime is minus x sine theta plus y. Well, it's got to be cos theta. I know that you never get sine. That is a little bit of a help. Now, I don't know about you, but ever since day one, I've had trouble proving this theorem. And it's not particularly hard to prove, but I get messed up with all the angles and, you know, I'd like add this length to this length and try to figure it out that way, right? By breaking it down into these additions of little bits, like this bit plus this bit and so on, because they're related. And you do eventually arrive at the answer. But if you use the dot product, use the dot product method I'm going to show you now, there's nothing to this. Absolutely nothing to it. First off, you will note that the vector p drawn in either coordinate system as we're viewing it now overlaps, and the position p overlaps, right? So although this is maybe a general truth, just numerically speaking, yeah, the following is true. I'd like to use this box, but it's on. Okay, I'll use this box for theorems and stuff. P here I can write in the following way. P equals x hat I, right, plus y j hat, right? Oh, I'm not going to finish it yet. I'm going to keep going. But it's also equal to, if we imagine hat I and hat j in our xy system, equivalently we can have a hat I and a hat j in the prime system. So I can say x prime hat I prime, the primed hat I, y prime hat j prime. That happens to be true. White or a new color? Maybe a new color. This one. Make a lot of space. Now that certainly is true if you invented a unit vector to go along the x prime axis. Let's say it goes to here. I found I put a space between them and it looks okay. We'll call this hat I prime, and we'll make another one in the y prime direction. You don't see the prime if you don't put a space. It's almost invisible. So equivalently, we can make I prime and j prime in the other system, and we can express the point in the in the prime coordinate system in that way, right? I'm going to show you now how easy it is to prove that theorem using the dot product. Okay, I'm going to take this equation, okay, we'll start with, we'll go 1 to 4, or I'll do at least 1, and you'll get the idea. I would like an expression for x, so I don't want to see y. Okay, so what I'll do is I'll take the dot product of both sides with I. Okay, the I is this one. I don't know what's going on with that. Right. That's I, right? And J is here. Right? And I'm going to dot product both sides with I. So that means I dot J is 0, so immediately I have an expression for x. X equals, because I dot I is 1, x prime times the I prime unit vector dot I plus y prime times j prime right? Because of the distribution law we discovered, and the fact that I and j are perpendicular, instantly we have at least an expression for x that has x on this side and only prime stuff on this side. Now all we got to do is figure out these dot products, which are easy. Let's see now, I prime dot I. Remember that the dot product of two vectors is the the magnitude of the two, 1 in this case, times the cosine of the angle between them. So I prime dot I is cos theta. So this is x prime cos, this is cos theta. I'll put the theorems over here. Well, it's commutated. And in yellow. That just happens to be a fact. The product is cos theta, because the magnitude of each is 1, and the angle between them is theta. Okay, what about j prime times I? That's what we need here. We should also note that the angle between these two axes here is the same as this. It's easy to show. That's the only bit of geometry you need. Okay, what's j prime dot I, or I prime dot j? Well, I and j, it would be 1 again times the cosine of the angle between these two, right? Okay, well, this angle is theta plus 90 degrees, right? So yeah, that's exactly right. So it's 1. So j dot I is just the cosine of pi over 2 plus theta. I prime, I prime dot j. That's what we want. No, it's I, sorry, dot j prime. Alright. I, j, 1 times 1 times cosine of angle between them, with the cosine is, which is the cosine of pi over 2 plus theta. Now it gets you into the problem of remembering remembering the addition rules for cosines and sines. Well, let's see. It's going to be sine, either plus or minus sine of theta. Right? Question is which. It should come out to be negative because we can see it here, but let's see. Pi over 2 would be moving just pi over 2, a point here of x equals 1 would go here. And if we add it a little bit, the cosine is changing signs, as it should, and adding makes the cosine negative, or the cosine of this for theta would be a negative value, right? If I the cosine being the x of something, usually like x and y. X is our cos theta. If I were to express an x value in those terms, and x were here like 1, and the angle was pi over 2 plus a little bit, that value would be negative, right? So it's got to be equal to minus sine theta. Yellow. Doesn't fit. Well, we'll put it down here. So I dot j prime is minus sine theta. So now we have proven the first one. X prime, I prime dot I cos theta minus y prime sine theta. So we're done with this one. I don't have a check mark. I don't remember my check mark. But I gotta put some indicator that it's done. There you go. So that's proved. So now, doing the rest of them is just as easy. All I do now to get an expression for y is take the dot product of both sides with j. Okay, and that's going to give me immediately, I can write down y equals x prime times at I prime dot at j, right? This is multiplying by plus y prime at j prime at j. we can write that down immediately. The j kills off this one. Now j dot j prime is cosine theta. See? And it's not that hard to figure out what I prime dot j is. We have I dot j prime, I prime dot j, which is this dot this, right? Is going to be 1 times the cosine of the angle between these two, which is again pi over 2 minus theta, right? So cosine of pi over 2 minus theta happens to be equal to plus sine. Well, I know because I'm looking here, but it's easy to show, easy to figure out by sort of imagining again what happens to an x position when you subtract some theta, right? It remains positive, so that's the plus one of those things. Or you could try to remember the addition formula, which I have a proof for, but probably not enough time or space to do it. But anyway, just in my head, I've already done that one. X prime, so it's cosine of pi over 2 minus theta, which is sine theta, plus y prime j dot j prime is cos theta. So 2 is proved. See how easy that is? Well, the other one that we just found there was that is this one. So I think, and also j dot j prime, and that covers all the mixtures, I think. Right? If we're doing it the other way around, we'll be multiplying by, if we wanted to get x prime, we would dot product both sides by j prime, and we'd have I dot j prime, which we've got, right? So therefore the x term is minus sine theta times x. Well, look at that. Oh, wait a minute. J prime. Oh, that's for the y. So that's correct. See? Multiplied by j prime, this one disappears. You get y prime. You get a minus sine theta times x and y cos theta. Similarly, multiply those sides by I prime, and you get x prime equals x cos, it's going to be x cos theta, because I know those, and the y is I prime times j, which is sine theta, so plus y sine theta, and we've got all of them without using any geometry. Okay, just thought you might find that interesting. There are other things I can prove that I would like to show you using the dot product. And there's another kind of product that, but I don't have time to get to it now. Let me save this. This should save fine now. I forgot, and whoops, I forgot. And these can't be saved as ANSI. They have to be UTF-8, but it should come back. We'll rotate this one. Yeah. So, oh, I'm missing a vector. Okay, no problem. No, I'm redoing all that stuff. Okay, see you.